The next specimen is tail with extensometer. So now he is using a different Syntec 10GL setup, but the functionality is just the same. Oh wow, so this is the extensometer that we will be gripping on the specimen. And this is the pin. So he removed the pin and now he's showing the movement of the extensometer. So there's a spring on the left side that will make sure that the ends of the extensometer hold on to the specimen. And he's showing the movement of the extensometer on the test work software. So we can see how sensitive that is.
And now he has to adjust the jaws as usual. As you see, this is a new equipment. This is a new test setup, and the specimen is being loaded exactly the same way, first at the top, so that the load is taken into account, the load of the specimen, and that will be nullified later. So it is adjusted in the same way, the jaws are tightened, and then...
Also look at his headband. That is like from 1970s basketball player, right?
Except that he fixes steel specimens onto jaws.
Yes. The extensometer is a delicate equipment.
So one must be very careful handling it.
Oh yes.
So here we can see that the load is being adjusted so that it gets to a certain value. And then we have to fix the extensometer at a certain position.
So now he's inserting the pin back in the extensometer before gripping so that the gauge length is 1 inch. So the pin is inserted and now he's gripping the extensometer using the wires that will grip the extensometer on the specimen. And now we should make sure to look at the extensometer from all possible angles so that the gripping is vertical and it's near the center of the specimen, because that is where we expect the failure to be, right? And when he's sure that the gripping looks good, he's removing the pin of the extensometer.
So what's the use of the pin, by the way?
The pin makes sure that the gap in the extensometer at that point is 1 inch, which is the gauge length.
And then that will be used to measure the strain.
Yes. So the extensometer output channel on test works is the strain value. It's not displacement, it is extensometer strain. The units are inch per inch. Whereas for the crosshead, it is displacement.
Wait, did he make a mistake?
Oh yes, he forgot to click on the lock button on the handset.
Yes. So now that we are ready to go.
So the software is reminding to remove the pin from the extensometer, otherwise it might damage the extensometer if the pin remains inserted in the extensometer and if we start the experiment.
Which we have done already.
Yes. Do we need to zero the crosshead displacement channel?
No. The
Yeah.
machine automatically zeroes it, right?
Yes. Once we click on start the experiment, it will automatically zero the crosshead displacement to 0.
We're showing you a second screen just to emphasize that the specimens are in place, extensometers are in place, and the test is about to begin.
Yeah, so it entered the dimensions and it started on start the test, and notice how different are the values of the crosshead displacement and the extensometer strain.
Yeah, the readings are quite different.
The extensometer strain is only 0.0004, whereas the crosshead is 0.04. So does this mean that the crosshead is not accurate? No, right? The crosshead is accurate, but crosshead is measuring the deformation of many different materials, which are, because of the load, there might be some deformation in the jaws, in the load cell, or other components of the setup. Whereas the extensometer only measures the deformation in the specimen. So extensometer is measuring localized displacement. Therefore, it is more accurate. So at this point, there is a message, remove extensometer now.
So we need to remove the extensometer at this point in
Yes,
order
so
to
the
make sure that it is not damaged.
yes, so we have just crossed the elastic region and the specimen has just entered the yield region. So we need to remove the extensometer at this point, and we can verify that we have crossed the elastic region by looking at the graph in the test work software, which we cannot do in the video, right? Well, we can do it right now.
Yeah.
So now we have just entered the plastic region. We are in the yield region.
And as you can see from the two videos over here, the specimen is undergoing in the test, and then we are about to see some different values, and we'll probably see a failure. What do you think?
Oh yes. So now this is exactly the same as the earlier experiment on A36 without extensometer, right?
That's correct.
So we should see a failure at approximately the same load, which is about 7,000.
Oh, what if this is machined differently, this specimen? What if failure does not happen because the design capacity is 10,000 pounds? Well, let's see.
Let's see about that. We can see that the cross-set displacement is increasing at this point, as well as the load.
Wow, the load value is
Load value is increasing at this point.
6,500 pounds, huh?
Yes, and that's pretty much close to what we had studied when we did the A36T.
The same specimen, but without extensometer.
That's correct. So you can see that the value is increasing for both, and
We have not reached the ultimate strength point then.
yes, we haven't reached it yet.
So
And
there's
you can
no
see that,
necking.
and the cross section remains constant.
Wow, 6,800 pounds. We are nearing the value of 6,900 pounds. Maybe Ed might win his bet on this specimen.
Of 7,000 pounds.
Yes. Wow, so this is 7,000 pounds. Did you bet on 7,000 pounds?
This time, yes.
As you can see, the load value is reached at about 7,000 pounds, and the curve mostly looks like taking some detour, and the value is increasing. And with increasing, there
The value
is
starts to decrease now. So
And
we
there
have
is-
crossed the ultimate point, and we can see necking.
immediately when the values have slowed down, and we can see a break at any point now. Interesting mode of failure.
The cup and cone type of failure, huh?
As we've already seen in first test. So now we're checking the temperature, and it's pretty warm. A lot of thermodynamics going on.
Oh yes, Professor Dressler is teaching too much thermodynamics this semester.
That's correct.
I'm sure that he might have a question on the thermodynamics of the tension experiment in his class.
And you never know. That might happen. So we can clearly see the mode of failure here on the profile, which is a cup and cone shaped classical failure mode for a A36 steel specimen. So now that we have done, we need to save the data as usual, and this is the profile for the stress and the strain curve. So thank you for watching.